Hello everyone. I welcome you all for today's session on electromagnetic waves. 18EC55 for the video syllabus. Module 1, Coulombs Law, Electric Field Intensity and Flux Density. Lecture 1. I'm your friend Madhavas, Assistant Professor, Department of ENC, Gaussian College of Engineering. Before going to the detail, if you're not subscribed to my channel, subscribe to my channel, click on the bell icon for further notification, or share with your friends for the benefits. First, let's see the content, what we are going to cover in the first module. First one is Coulomb's law, electric field intensity and the flux density. In this, we are going to see the first thing is about experimental law of Coulomb. Then the second concept of electric field intensity. Third, field due to continuous volume charge distribution. Field of line charges. Field due to a state of charges. Then we'll see the electric flux density and some numerical problems. First, let us see what is experimental law of Coulomb. Coulomb is a scientist who invented the force exerted between two objects, each having a static charge of electricity. He then stated a Coulomb's law. The statement was the electrostatic force between 2-point charges Q1 and Q2 is directly proportional to the product of the magnitude of the charges and inversely proportional to the square of the distance between them. This is the statement what was given by a Coulomb. Now let us understand the mathematical representation of that. So you can observe these are the 2-point charges represented by Q1 and Q2, and the distance between them is given by capital R there. And the statement is mathematically represented as F is directly proportional to the product of two charges Q1 and Q2 and inversely proportional to the square of the distance between them, as we can observe the statement. So let's consider this as equation 1. Okay, so this proportionality constant is replaced with the help of K, where K is 1 by 4 pi epsilon naught. Okay, so where epsilon naught is permittivity of the free space, and the value of the epsilon naught is 8.854 into 10 raised to minus 12 farad per meter. And the unit of the force is measured in terms of Newton, and it is denoted by capital N. And whatever the units specified here are all measured in terms of standard unit, SI units. Now let us see the explanation in terms of the vectors. So let's see, let us represent the Coulomb's law in a vector form. The direction of force F12, you can observe the notation here, the top of F is given an arrow mark. It indicates the direction of the force in which it is moving. Is shown because Q1 and Q2 are considered as same charges. Now let us see that. So you can observe Q1 and Q2 is of same charges. When same charges are brought nearer, it gets repelled. And the distance between them is given by R12. So we have a reference point called as origin, and the distance from charge Q1 and Q2 with respect to origin is small r1 and r2 there. So if you can observe, r1 is the distance of Q1 from origin, and r2 is the distance of Q2 from the origin. So from the figure, you can observe force F2 or F12, that is force from 1 on 2, has to be calculated. That is, whatever the destination charge is there, that is being given as a suffix F2 is the force on Q2 exerted by Q1. And from Coulomb's law, we can state that F2 is equal to Q1 Q2 divided by 4 pi epsilon naught r square. We are just adding the vector notation called as A12 arrow mark. It's a unit vector representation here. So A12 is the unit vector in the direction of R12. So this is the experimental way of representing the Coulomb's law with the help of vector form, where A12 is the unit vector in the direction of R12, and it is given by a definition of that's the distance between the R12 and the modulus of R12. This is a standard definition for the unit vector, where R12 is the distance between Q1 and Q2 given by R2 minus R1. That's the distance of Q2 of the reference from the origin, and R1 is the distance of Q1 from the reference of origin there, where R12 is the vector quantity and modulus is the magnitude of that particular vector, and the unit vector is given by vector by magnitude there. And this is the general definition of the coulombs represented in the form of vectors. Now let us see the second concept, that's about electric field intensity. The term itself says what is the intensity at which it is experiencing or it is exerting a force on the other charges. As we know, a charge is having an electric field around it. So the concept of electric field intensity came into an existence due to an electric charge. As you can observe here, the center point is given as positive charge. So an electric charge always sets up an electric field around it in its surrounding, and it exerts a force upon any other charges which arrives in this field zone. So as we have seen in the previous one, two poles, there is two charges of same polarity gets repelled. Why it gets repelled? When the second charge enters this particular region around the positive charge, depending upon the polarity, it exerts the force there. If it is negative, it attracts it. If it is positive, it gets repels. Therefore, the field zone is called as electric field intensity, at what intensity it is performing the operation there. So this electric field intensity is defined as, the definition is given as, the electric field intensity at any point in an electric field is the force experienced by a unit positive charge placed at that point. Now, if you bring a unit positive charge and place it at the surrounding of this charge, that particular unit charge experiences a certain amount of force, and that force what it is experiencing is called as electric field intensity there. This is the definition of electric field intensity. If we now consider one charge fixed in a position, say q1, and move a second charge slowly around it, it experiences a force in this region around the charge q1, which is given by, as we can observe in the Coulombs law, we have taken two fixed charges of q1 and q2. Now what we are doing here is that we are keeping one charge fixed and we are bringing the second charge near to the q1. Then what is the force experienced by that is given by a definition of q1 into qt divided by 4 pi epsilon naught rt square. That's the target there, where qt is the second charge. Now if we consider qt as a unit charge, then the force per unit charge is given by, so bring this qt to the denominator here, it is given as q1 by 4 pi epsilon naught rt square there. That's the second expression what we have. This force per unit charge is called as electric field intensity, and this is the definition of the electric field intensity there. So we can denote this force by qt as electric field intensity, and it is also given as q1 by 4 pi epsilon naught rt square there, where is the electric field intensity, and the unit is represented by Newton per Coulomb, general way, or frequently used is joules per Coulomb, or in general representation we represent that in terms of volt per meter. And this is the electric field intensity definition what we have. So electric field intensity at a point due to many charges. So as we have seen in the previous concept, we have brought only one point charge, that's a unit positive charge near to the second one. Now if you bring a large number of charges, then what intensity that particular charge exert on the other charges is the concept what we have to derive here. So the field at a point when there are many charges contributing to the field can be found by employing the principle of superposition. Superposition means we have to add all the charges which is exerting a force on that particular charge. So if there are more than 2 point charges, then each will exert a force on each other. Then the net force on any charge is the principle of superposition. As we already know, each charge is surrounded by its field of energy. So when they come together, they experience a certain force there. And the net force experienced by that one is called as the principle of superposition. So we can see here a reference charge as Q, and Q1, Q2, Q3 are the other charges which is coming nearer to the charge Q there, and has the respective distance of R1 to Q1, R2 for Q2, and R3 for Q3, and R the distance of reference charge Q through the origin there. Now we need to find the distance between Q1 and Q3, Q2 with reference to the origin. There is a reference charge Q there. So what is the net force experienced by this particular charge Q due to the Q1, Q2, and Q3? And this is what is superposition. As we know, superposition, it is a summation of all the forces experienced by that. Now, since we are calculating the electric field intensity, the total electric field intensity is the sum of all the charges exerting on the charge Q there. So in the figure, we can consider three charge Q1, Q2, and Q3 with electric field intensity E1, E2, and E3 respectively. For so on, we can go for N charges. So the total strength of electric field intensity is, we have to replace the E1 with Q1 by 4 pi epsilon naught R minus R1 modulo square A1. A1 for respective unit vector. Similarly for Q2, A2 divided by 4 pi epsilon naught R minus R2. Q3, A3, 4 pi epsilon naught R minus R3 square. Like that Q1, AN divided by 4 pi epsilon naught R minus Rn square. Now when take the common parameter, what we can just say, M is varying from, so here M I can write it as varying from 1 because this is the minimum and the highest value is N. So N, so it is E is equal to summation of M is equal to 1 to N is equal, that is Qn into AM divided by 4 pi epsilon naught R minus Rm square. So this is the effect of large number of charges on that particular charge. So what is the net electric field intensity exerted on that particular charge due to a N number of charges coming to it? So if you have any questions, write down your questions in the comment section. I will reply to your questions. If you're not subscribed to my channel, subscribe to my channel, click on the bell icon for the notification, or share with your friends for their benefits. Thank you.